This will be a quick video on rotary encoders. I've hooked up my oscilloscope. I'm using this device here. These are commonly available. They are a rotary encoder assembled to a circuit board that includes resistors on the back there. These are for the purposes of pulling up the signal. Eventually we'll hook these to an Arduino device. Those have built-in input pull-ups, so the need to power these becomes irrelevant if it's configured correctly. I've got the same device on my breadboard here. I have my oscilloscope connected to the clock pin and the data pin, and then I have a power supply powering the board from ground and positive, and I'm powering it with 5 volts. When I turn the rotary encoder, we get a series of pulses. Here I'm turning it counterclockwise. If you look carefully, you can see that the signal from the top trace goes low prior to when the signal from the bottom trace goes low. The opposite is true when I turn clockwise. You can see that the signal from the bottom trace goes low before the signal from the top trace goes low. And this is how we determine which direction the encoder is turning. So to decipher these signals on a device such as an Arduino, we need to understand the position of both of these pins over time in relationship to each other. A common way to do this is to continuously scan the input pins. Our pins here connect to these. They're kind of like brushes on a motor. It's kind of hard to get on my phone camera here, but there's places that are blank and then there's places that connect those wires together, and as we turn it, it connects those wires in determined sequences. So this is essentially a completely mechanical process. So I found and modified a simple rotary encoder reading sketch here. I have 2 pins defined. One is the clock, one is the data. Those are just connected to the pins on the rotary encoder. Of course, the grounding pin on the rotary encoder is connected to ground. There's not much going on in this. Our loop reads one of the pins and it compares it to the previous read and then compares it to the other pin and makes a determination on whether it's clockwise or counterclockwise, and then it prints on the serial monitor a direction and how many positions it's moved. And that's really all there is to it here. Let's run this. I'll open the serial monitor. Now when I'm moving counterclockwise, you can see it's counting pretty well. I can go fairly fast with this even, and it's reading consistently. All of the examples that are running will be put together, zipped together, and placed on my Patreon page. You can download it. You do not have to be a paid member to access this information, so just go ahead and download it there if you're interested in following along. There's a link in the description box. I've expanded my setup. I have a TM1637 display so we can see what's going on. There's 2 rotary encoders connected to pins 5 and 6 and also 7 and 8. We're only going to work with one of them for now. I'm using the encoder library that's freely available, as it does a lot of the background work for us. All we have to do is make an instance of the encoder with the pins that we're on, and then read it every cycle, and then it goes out and it does the job that the previous sketch that I showed you does for us. So before we start with this, I've made some changes to the loop here. It counts how many times the loop is run. Every 2 seconds, this is 2000 milliseconds, every 2 seconds it will tell us how many times the loop executed. This will give us an idea of how many times the loop is operating per second. So let's run that and see what we get. I'll open the serial monitor, clear the data, let's see what it starts sending us. You can see every 2 seconds it's sending how many times it went through the loop. Looks like almost 290,000 pretty consistently. That's a pretty good number. If we're looking at the pins on a rotary encoder, 289,000 times per second, we shouldn't rely on luck very much to make sure we're there at the right time to see the data that we're interested in. The Uno board that I'm using has a 16 megahertz clock. So we can do a little math on this. We'll divide 16 million divided by 289,000, and we can see that each time we loop through, it's taking about 55 of those processor ticks. That makes sense based on the fact that I'm incrementing a variable, I'm checking the time, I'm comparing the time, I'm doing some math, and I would expect that would be about 55 clock cycles. Alright, but we're not doing anything other than counting loops at this point, so let's start scanning our rotary encoder. I'm only doing one of them at this time, so we're going to ask the encoder library to scan it and see if it found anything new for us. So let's run this. And clear our serial window. Oh, okay, now we're getting 134,000 cycles per second pretty consistently. Do a little math on that. And now every time we loop, it's going through about 118 processor cycles. 134,000 times sampling the pins on a rotary encoder is still probably going to be just fine for us. We don't need a whole lot of luck to make sure that we're there in time to see the data that we're interested in. Well, let's add another one. Now I have my 2 encoders set up, and we'll run this again. And back to our serial monitor, we'll clear that. And now we're down to 68,000 times per second. It's probably still usable, but we might experience times where we move it and it doesn't catch it at that very moment in time. And as we add more processing, we're not even doing anything yet really with this data, so let's add something that does. Alright, I've changed this to only read the one encoder. We're going to determine if any change has been made to it, and then we'll display on the LED display if anything has changed. Still pretty simple. It's still also tracking how many loops are executing, so let's run this. Clear the output. We can see that we're still scanning at 113,000 times per second. That's still pretty reasonable. If I change my encoder here, we should see it update on the display. I'm getting a little bit of inconsistent results unless I go really slowly. Looks like clockwise is working pretty well. Let's start adding more. So I'm going to start processing encoder 2. Alright, so now we're looking at both of the encoder 1 and encoder 2 to see if any changes have been made, and then we're going to print on our display the 2 numbers. So let's run that, see what happens. And now we're executing at about 70,000 samples per second. Let me change this here, see what we get. Starting to get even more inconsistent. I have to go pretty slow to get good numbers. Every detent on this type of encoder is giving me about 4. If I go too fast, it starts to not be reliable. If I go clockwise with it, it's a little bit more reliable. Try the other one. And same thing, if I go counterclockwise, it starts to miss data that it's interested in, that we're interested in. But it's still working and probably usable for a lot of applications. I'm going to note here also, if we put any kind of delay in our code, that this is probably going to just become unusable. it's definitely not working the way we want it to. So no delays. But a delay could also be things like other code that's running that takes a while. For instance, displaying, if I were to run the display show string every cycle, it would bring it down to about the same amount of time. So sampling of the pins becomes problematic depending on what else we're trying to do with our code. So what are the solutions? The easiest way to solve this problem is to use pins on your Arduino that are capable of producing interrupts when things change on them. On the Arduino Uno, we have 2 pins available that do this. They're pins number 2 and 3. On the Mega, we have 6, and you'll have to look up other boards to see. Some of the more modern boards have a lot more interrupt pins available. You'll have to check on which board you want to use. For this example, I'm using an Uno, so we're going to remap one of our encoders to pins 2 and 3 and see how that affects our performance. In my sketch here, I have one encoder on 5 and 6. I'm going to move it to pins 2 and 3. What this does is it allows us to not have to sample the encoder every time. In fact, I could take this out and it would still have an effect. So now it shouldn't matter if we're looking at it every cycle like this. It should update regularly and consistently. Let's see if it works. I'm getting very consistent results when I move my encoder clockwise and counterclockwise. Where the one on the right is a little more erratic because it's not on interrupt pins. With the encoder library, you could actually hook up only one of your pins to an interrupt pin on each encoder, and that improves your performance substantially as well. So if I move, for instance, if I put this one on 2 and this one on 3 and then this one on 4 and this one on 5. So one of them is going to be on 2 and 4. The other one is on 3 and 5. There's no real substantial change to the time there, but now when I move these, they work really well. Problem is we only have 2 interrupt pins. I'm also going to note here that we could actually take these out of the loop. So I've updated the program here. It does not read the encoders every time it loops. I have it reading only every 2 seconds, but it should update okay because they're on interrupt pins. When the pins change, it actually goes out and samples it automatically for us within the encoder library. So we can read it whenever we want, and it should be relatively updated. So if I turn it now, it'll take a couple seconds potentially for it to indicate the change, but there I changed it, and about 2 seconds later. You can also see that we're back to about 160,000 cycles per second, only because we're not reading it every time. If our sketch is busy doing other things and we still want reliable reading on encoders, we can use the interrupt pins to make that happen, and it's working pretty well here, even with just one interrupt pin on each encoder. So that's one solution you have, but we only have 2 interrupt pins on an Uno. There's 6 on a Mega, so if that becomes a limiting factor for you, we'll talk about advanced options in the next video. If this type of content interests you, make sure you subscribe to my channel. I'm also on Patreon, and that's one of the places that I share my example codes with you. You do not need to subscribe to get it there. We also have a Discord server where you can talk to me directly, as well as other friends of the Curiosity Workshop. So we hope to see you in one of those places. On the next video on encoders, we're going to talk about advanced solutions for dealing with multiple rotary encoders. Thank you for watching.